Hi, this is Matt McCormick. I'm in the philosophy department at California State University, Sacramento. This is my second lecture on Ian Hacking's Chapter 3 from Introduction to Probability and Inductive Logic. We've been talking about gambler's fallacy, bias, independence, dependence, and I'm going to introduce a new concept in this lecture called fairness. All right, so what's a fair system? We need to understand fair systems to be able to do probability stuff from here on out. So we've got a technical definition that we want to invoke for fair. You've got an intuitive definition, which you know about fair, but our technical definition involves two technical concepts, bias and independence. So formally, a fair system is one that is unbiased and independent. So last time we learned a lot about dependent versus independent systems. Let's talk about biased and unbiased systems. So we say that a system like a flipped coin, a thrown die, a single thrown die, or a spun roulette wheel, a song shuffler maybe, or a winning lottery number, those are all unbiased. And what we mean by that is to say that the relative frequency in the long run of each possible outcome is equal to that of any other. It is biased if the frequencies of the outputs are different. So the easy intuitive example here is a single six-sided die. If I take a single six-sided die and I roll it over and over and over again, the outcome, the probability of getting any one of those sides, a 1, a 2, a 4, a 5, a 6, the probability of getting any one of those is 1/6. So all of the relative outputs are the same. If I roll two dice like you do when you play craps, and I roll them together and we take the sum of the faces, then the outputs are actually biased. That is, the relative frequency in the long run of the outputs are not the same probability. A 7 is by far the most, not by far, a 7 is the most probable outcome when you roll two dice together, because there's the most ways to get a 7 when you roll two dice. There's only one way to get a 2, only one way to get a 12, but there's 7 ways to get a 7. You can get 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, and 6 and 1, counting the first die and the second die. So there's all these different ways. So two dice produce a biased outcome, where the most common or the highest probability outcome is 7. And you can see from my chart over here that 7 is about 17% probable, whereas getting a 2 or getting a 12 is 2 or 3% probable. Okay, so a single die is unbiased. Two dice thrown together and summed the faces is a biased output. So what about the frequency of outcome for throwing two dice like craps? Craps is biased in that the relative frequency for each possible outcome is not equal. The frequency for 7 is higher than the others. But rolling a single die is unbiased. The relative frequency of each possible outcome is the same. Okay, so that's our formal definition of bias. So to remind us now about dependence and independence, we talked about this last time with gambler's fallacy. Trials or events are independent if the probability of the outcome of one is not altered or does not depend on the outcomes of the other trials. So in the case of dice, either 1 or 2, rolling one die or two dice, those are independent outcomes. The earthquake example I gave you last time is a dependent probability. So as time goes on and the earthquake doesn't happen, the probability goes up. Or if I draw a card from a deck, a well-shuffled deck, and I pull an ace out of the deck, and I take the ace out and put it aside, now what are the odds of my getting, say, another ace? Now my odds of getting another ace are 3 in 51, whereas before they were 4 and 52. So the odds change from one to the next. That means it's a dependent probability in that kind of procedure. If I had taken the first card out of the deck and looked at it and then put it back in the deck and reshuffled it, the second probability would be independent of the first. Okay, so that's our other crucial notion here for our concept of fairness, is that a fair system has both independent and unbiased outputs. So if the odds of a future event are not changed by the current event, that's the more formal way or the more abstract way to put it, then the procedure is independent. Independence is the key notion to something's being random as well. And random systems or random outputs is another concept we're going to talk about today. When a series of trials are independent, we often say that the series has no memory. I talked about that last time with the die doesn't remember what it did before. The universe is not trying to push through and push a tails out of your flipped coin. The coin doesn't remember. It has no record of what it did in the past. In such cases, all perceived patterns are usually illusory. Coin tosses are independent. Taking a card out of a deck, checking to see if it's the ace of spades, and then setting it aside before you draw another one is a dependent procedure because the first draw affects the odds of the next draw. The odds of getting the ace of spades was 1 in 52. On the second draw, it's 1 in 51. That is if I didn't get the ace of spades on the first draw. So suppose I pull out a king, and now I've got 51 cards left. I'm still wondering, what are the odds of my getting the ace of spades? Now it's 1 in 51. Suppose I pull out 10 cards. Now I'm down to 42 cards and I haven't drawn the ace of spades. Now my odds of getting the ace of spades are 1 in 42. And what would happen is the odds would continue to get bigger and bigger and bigger until I hit it, until it would be a certainty. If I drew 51 cards and didn't get without replacement, and I did not get the ace of spades, then the last one would have to be 100%. The last one would have to be an ace of spades. Okay, so the example, the case we always use in inductive logic and probability classes is we usually talk about an urn. Fair procedures, we've said, are both unbiased and independent. The standard example of a fair procedure is an urn of marbles with equal proportions of different colors that we can sample at random. So imagine I've got 50 black and 50 red marbles in this urn. So that means, suppose I shake it up, I reach in, I pull a marble out, I look at it, it's black. Okay, I put it back in the urn and I shake it up, I reach back in. Now, what are the odds of my getting a black marble? They're 50%. It's independent, it's unbiased. This is a fair system if I keep doing it like that. If there were 80 red marbles and 20 black marbles, this system would be biased because the relative frequency of the two outputs is not the same. If it's 50-50, then it's unbiased. If there were 30, suppose we had 100 red, 100 black, and 100 yellow marbles in there, that would be unbiased. But as soon as one of those numbers gets different than the others, now the system becomes biased in its outputs. If you were going to try to base an estimate of what sorts of marbles are in the jar on a sample, you would need to do sampling with replacement. And that would ultimately, well, I suppose if you did it without replacement, you just took them out one at a time, one after another, you'd ultimately get all the marbles out of there and you'd find out what was in it. You'd know what the nature of the population was. This means blindly drawing a sample, replacing it, shaking the urn, and then drawing another, or we talked about with and without replacement for a deck of cards. So replacement here makes the difference between the outputs being dependent or independent. And it could make the difference for the outputs being biased as well, depending on what we're looking for. Putting the marble back in keeps the relative frequencies of all the marbles the same for each subsequent draw. Okay, so for example, and I actually love this. I love this case because it illustrates sort of how new and how novel our understanding of probabilities are. As a science, probability theory is just a few hundred years old. If you had gone back to ancient Egypt, we've got archaeological evidence that they played a game like dice using sheep ankle bones. And what's interesting about these ankle bones is that when you throw them, they don't come up at an even, unbiased outcome. So some sides are more likely to come up than others, which makes for a biased output. They have four sides, but they don't come up evenly because they're not uniformly shaped the way a die would be. So it's a biased system, even though the rolls might be independent depending on how somebody's rolling those out. But what's amazing is that the people didn't seem to think that it mattered. Like in ancient Egypt, 3500 BC, there's no evidence that they apportioned their betting behavior according to the relative frequencies. So I take it that archaeologists have discovered that they've got some evidence about the way they were betting on these bones, and it doesn't look like they were betting on, suppose one of those sides of the ankle bone is more likely to come up than the others. It doesn't look like people were betting on that side more than the others. Like they just didn't put it together, they just didn't see it. So if you have a time machine, you could go back and clean up on the ancient Egyptians with your modern 21st century knowledge of probability theory. Okay, so to say another word about gambler's fallacy from last time, Hacking points out that when someone commits the gambler's fallacy, he or she is basically being inconsistent. And what they're doing is the gambler stipulates that the system is independent, but then relies on the past performance of the system to predict its outcome. Or the way I've been characterizing this is that the gambler is mistaking an independent system for a dependent one. They think that because a tails hasn't come up, that the universe or that the coin is pushing for tails, that there's a cause that's happening from the past that's reaching into the future and making that output more likely as you move forward. So the gambler's fallacy now more formally, to tune up from my looser definition from the last discussion, is we commit the gambler's fallacy when we mistake a random number generating system with independent outputs for one that doesn't have independence, or one that has, we think it's dependent. The gambler mistakenly infers a causal connection between trials when there isn't one. Gambler's fallacy is a matter of independence, not bias. There's a bunch of other interesting gambling mistakes or fallacies or problems that we could talk about. And there's different things going on there that's maybe related. But if you go to the casino and just watch, you'll see people doing all sorts of interesting things. They'll rub the machine in certain patterns, or they'll get up and sit down or do certain sort of ritualistic behavior. And I think I'd want to talk to somebody about this, what's going on here. But I think this is not unlike the thing we see with like professional sports players who will win a playoff game in the World Series or something, and then, or they'll go into the playoffs and they'll refuse to cut their beard, or they'll refuse to change their shirt, or they'll refuse to do anything different, or I always have to eat spaghetti the night before the big game, or whatever. People get into these kind of strange ritualistic behaviors. And I think what's going on here is that evolution was working to build a system that once you get it up and running, it keeps itself alive. And it keeps itself alive by aggressively and over-eagerly trying to find the causal connections in the world and trying to quickly piece together what the hell's going on out there. You know, you're always moving through the world not knowing where you're going, what's coming next. You know, the world's full of surprises. So evolution built these organisms that are trying to figure out what the hell's going to happen next. And they're looking for, over-eagerly looking for connections. Oh, well, if I do this, then this will happen. If I do this, then that'll happen. Or don't do that again because that'll happen, right? So you make connections, causal connections, more of them than are actually there, which sometimes works to your advantage. If you fail to notice a causal connection about something that will feed you or something that will kill you, then obviously that's got a heavy you're going to pay a heavy price for that, and that sort of cognitive mistake is going to get weeded out of the gene pool. But the mistake of finding too many causal connections pays off a bit better than not finding enough. So, according to error management theory, which we'll talk about some more later, the idea is that these two different kinds of errors, either underestimating causal connections in the world or overestimating them, one of those costs more than the other systematically. So evolution puts a pressure on the cognitive system to find more than really are. So that means as you're walking around, as you're dealing with stuff in the world, as you're interacting with objects in the world, your system is prone on the high side to find more causal connections than are really there. And I think that's partly what's going on with the gambler who is doing something funny on the slot machine, or has some ritualistic behavior, or is rubbing a lucky rabbit's foot, or putting something in their pockets, or whatever. And the same thing maybe with the sports star who refuses to cut their beard, or refuses to change their clothes, or they eat the same meal before every big match because, hey, it worked last time and I sure want it to happen again because I want to win the playoffs, or I want to, score dinner again, or whatever, if you're a Pleistocene hominid. So it makes sense in evolutionary terms, and I don't even want to say it's a mistake. It's a survival worthy trait. It's millions of years of evolution have crafted this system that has certain kinds of biased behaviors, and now I'm using bias in a slightly different sense than I just used it, but it's got certain sorts of behaviors that tilt one direction or another, and those tilts or those proclivities tend they lean towards, or they trend towards survival. They trend towards you making it. So we can understand the pitcher in the baseball team, or the coach for the basketball team who won't change his jacket, or somebody who won't cut their beard, or somebody who wants to have the same meal. You understand that they're trying to lock onto how does the world work and what can I do to control it. So I get it. We can be sympathetic with it without necessarily judging it, but we can also do better by understanding what's going on in the case. Okay, so let's talk about randomness. And here's another thing that this is the field in which this over-eager cause finding system is operating is the random world. So the world's got all this random stuff that occurs. So look at these two cases. Which of these was generated randomly? We tend to think of randomness as being more uniform and evenly spread out. So is the image on the right random, or is the image on the left random? Now, I think when we're being uncritical or unreflective, we sort of expect randomness to not be very random. We think that randomness should be more like on the right. We think it should be a little more homogeneous, a little more evened out, a little more uniform and spread. But actually, what happens in the real world, especially with you this little human and your little finite experience in this vast cosmos, is that randomness in the world actually clumps and clusters up. It bunches up into groups. So it leaves blank spaces and it leaves clusters. But that's actually random. That's when there's nothing going on. Shit just happens, or shit just doesn't happen, and there's no cause, there's no explanation. It's just randomness. But that hominid brain locks on to either the gap or the cluster and tries to build some story, some narrative out of what's going on there. So the first point here is that randomness, when random systems have outputs, they clump up, they cluster up. Although it's possible for anything to be generated randomly, it's much more likely that something's been generated randomly when it has clumps and clusters, rather than being uniformly spread out. Now, we start looking for a trend, or we start looking for an explanation, but it may just be that there's no data here. It's just a clump. It's just a cluster you happen to be in. So if we go back to our strings of heads and tails, for example, it's true that each of the following strings are both equally likely, but one is more likely to have been generated randomly than the other. So here's two. Look at string A, which is alternating heads, tails, and B got clumps and clusters of heads, then tails, heads, tails, goes back and forth. So the second one, these both could have been produced at equal probability by a coin flipped. The probability of getting this particular string A or the particular string B is exactly the same. But if I asked you a different question, which of these was more likely to have been generated randomly than the other, then the answer here is definitely B, even though the probability of those two strings from a fair coin would be the same. Okay, so that's weird. A truly random generating system is more likely to have produced B than produced A. Although the probability of getting either one of these is actually the same if you're predicting it ahead of time. So think of prediction versus postdiction. Prediction, if I asked you ahead of time, what are the odds that you're going to get this particular string, it would be the same. I think we've calculated this out from last time. It was 0.0009 or something like that. It's the same in both these cases. But if you look back at it and go, well, which one was produced by a random system, then that's probably B. If you had to bet, you should bet on B here as producing that. Okay, so another point here is that that's not hard to appreciate objectively, but it's harder to appreciate when you happen to be on the inside noticing a cluster. And here's my point here is, look at my two circles. So here's you with your small, finite experience, your limited, domain, your neighborhood, your town, your experience, your 72 years on the planet, whatever, and you occupy a little corner of the universe that might be either one of these two circles. And notice that from our perspective, this whole big array looks random, but for the individual who is occupying either the circle on the right or the circle on the left, the world looks really different to them, and it looks like there's something happening to both of them. One of them, it looks empty, the other one, it looks like it's full, and it looks like stuff's going on. So my point generally here is that randomness, especially on a vast scale, can look like, to us, if you're down in the local zone, can look like something's happening that's not happening. This is when randomly generated clusters start to look to us like patterns. It is why, for example, we believe that basketball and baseball players get hot or cold, or why we believe that clusters of disease in a particular area must have a cause. Your limited local experience with just a few data points is not representative of the world. Be cautious about assuming that your finite limited experience is representative of some trend or something going on the outside. I mean, the first question to ask is, what's the data? Is there evidence that something's going on that's beyond just my seeing something, right? Just beyond just my happening to see, two car wrecks on the way to work. Wow, what's going on? Why are there so many car wrecks? Nothing's going on. Just shit happens sometimes, and you happen to be on that road. Evolution built us to see more patterns and causal connections than are real. It looks like there's reasons why that would build a slightly more successful adaptive system. Okay, so let's wrap up the new concepts for part 2. We've now talked about biased and unbiased systems. In an unbiased system, the relative frequency in the long run of all possible outcomes is the same. In a biased system, the outputs occur at different frequencies. So that's like my example of an urn with, imagine you have an urn with 50 black marbles, 20 red, and 30 yellow. That's 100 marbles, but they're biased in their outputs because they're not all the same number. There's not the same relative frequency. Independent and dependent systems. In an independent system, the probability of an outcome is not affected by the occurrence of previous outputs, and we talked about that last time. Our example of a dependent system is like the earthquake example. An independent system is like the coin toss. Random number generation. Randomness is in reality produces clumps and clusters that often look like patterns from our local, limited, pattern-hungry viewpoint. Clumps and clusters. Reality produces clusters of heads or of sevens or whatever else we might encounter. These can look like trends or causes to our eager minds. And we've defined fair versus unfair systems. A fair system is unbiased and independent, and an unfair system is one that lacks either or both of those properties. So it's unfair if it's biased. It's also unfair if it's dependent, or both, neither. Gambler's fallacy, then, just to remind us, now more formally defined, is the mistake of thinking that the probabilities of a system are dependent when they are independent. And then in the last lecture, we talked about the myth of the hot hand, and this is this belief in winning streaks, usually in sports. Confirmation bias, we talked about briefly in the last lecture. That's the mistake of selecting evidence that supports a favored hypothesis while ignoring or neglecting evidence that would disprove it. All right, and that's the end of our lectures on Hacking's Chapter 3.